What if a star explodes near Earth? Not just any star, but one close enough that its dying breath could reach across the vast emptiness of space and touch our small blue world. Tonight, we'll explore what happens when the universe unleashes one of its most spectacular and terrifying events right in our neighborhood. Feel free to comment your time and location below. There's something beautifully humbling about contemplating stellar explosions while we're all scattered across this tiny planet, each of us under the same sky that has witnessed billions of years of drama. The visuals are here for you, but if you find comfort in closing your eyes and letting your imagination drift among the stars, please do. There's absolutely no problem if you doze off part way through this exploration. If you find peace in these gentle journeys through the cosmos, I'd be grateful if you'd consider subscribing and liking this video. It helps the algorithm find more curious souls like us who seek wonder in the darkness of space. Imagine looking up at the night sky and seeing something that shouldn't be there. A new star, blazing with the light of billions of suns, outshining everything else in the heavens. This isn't science fiction. This is what humans throughout history have witnessed when stars die violent deaths. And tonight, we're going to discover what would happen if such an event occurred close enough to affect our world. Welcome to a story of violence and beauty, where we'll explore not just the mechanics of stellar explosions, but the profound ways they shape the universe around us. This is the tale of what happens when stars reach the end of their lives and go out not with a whimper, but with a bang that can be seen across galaxies. Let's begin by understanding what we mean when we talk about a star exploding near Earth. In the vast scales of space, near is a relative term. The closest star to our Sun is Proxima Centauri, sitting about 4 light-years away. That might sound close in cosmic terms, but for a stellar explosion to significantly impact Earth, we're talking about something much nearer. Scientists generally consider the danger zone to be within about 25 to 50 light-years of our planet. Within this sphere of space around Earth, there are hundreds of stars, each following its own evolutionary path. Most of them will live quiet lives, burning steadily for billions of years before gently fading away as white dwarf stars. But some, the massive ones, are destined for a far more dramatic fate. These stellar giants, with masses many times that of our Sun, will eventually exhaust their nuclear fuel and collapse in on themselves with such violence that they explode outward in one of the most powerful events in the universe. This is what astronomers call a supernova. The word itself sounds almost gentle, doesn't it? Supernova, meaning new star. But don't let the pleasant name fool you. A single supernova releases more energy in seconds than our Sun will produce in its entire 10 billion year lifetime. It's an explosion so powerful that it can outshine an entire galaxy containing hundreds of billions of stars. Picture this drama unfolding in our neighborhood. One of the massive stars within 50 light-years of Earth reaches the end of its life. For millions of years, this stellar giant has been fighting a constant battle between two fundamental forces. Gravity pulls inward, trying to crush the star under its own immense weight. Nuclear fusion pushes outward, creating the energy and pressure that keeps the star from collapsing. It's a delicate balance, a cosmic dance that has continued for eons. But eventually, the fuel runs out. the star begins to create heavier and heavier elements in its core, from hydrogen to helium to carbon to oxygen, silicon, and finally iron. Iron is the death knell for massive stars. Unlike lighter elements, iron cannot be fused to release energy. Instead, fusing iron actually absorbs energy. When a star's core becomes primarily iron, the nuclear fires begin to die. Without the outward pressure from fusion, gravity wins the ancient battle. The core collapses in less than a second, shrinking from the size of Earth to a sphere only about 12 miles across. The temperature soars to 100 billion degrees. The density becomes so extreme that a teaspoon of this matter would weigh as much as a mountain. Protons and electrons are crushed together to form neutrons, releasing a flood of ghostly particles called neutrinos. Then comes the rebound. The collapsing outer layers of the star slam into this incredibly dense core and bounce back outward like a rubber ball hitting concrete. A shockwave races through the star at thousands of miles per second, tearing it apart from the inside out. In a matter of hours, a star that has existed for millions of years completely destroys itself in one final, magnificent explosion. The energy released is almost incomprehensible. In the first 10 seconds of the explosion, a supernova produces more energy than our sun will generate in its entire lifetime. The explosion is so bright that it can be seen from billions of light years away. If you could somehow survive standing on the surface of an exploding star, you would see a flash of light brighter than 1 trillion hydrogen bombs exploding every second. But here's what makes supernovas truly extraordinary. They don't just destroy, they create. In those final moments of stellar death, the incredible temperatures and pressures forge elements that cannot be created anywhere else in the universe. Gold, platinum, uranium, and dozens of other heavy elements are born in the heart of the explosion. These precious materials are then scattered across space, seeding the cosmos with the building blocks of planets and life itself. The calcium in your bones, the iron in your blood, the oxygen you breathe. All of these elements were forged in the heart of dying stars and distributed through space by supernova explosions. You are literally made of stardust, the ashes of ancient stellar fires that burned out long before our solar system even existed. Now imagine this drama playing out within 50 light years of Earth. The star explodes, and suddenly we have a new point of light in our sky, growing brighter by the hour. Within days, this beacon might outshine Venus, becoming visible even in broad daylight. Ancient civilizations would have seen this as a powerful omen, a sign from the gods that something momentous was about to happen. And in a way, they would have been right. The first thing to reach us would be the light itself, traveling at 186,000 miles per second through the vacuum of space. If the explosion happened 50 light years away, we would see the initial flash exactly 50 years after the star actually exploded. The light would arrive like a messenger, announcing that something extraordinary has occurred in our galactic neighborhood. But light is just the beginning. A supernova doesn't just produce visible light, it creates radiation across the entire electromagnetic spectrum. X-rays, gamma rays, ultraviolet radiation, infrared light, radio waves, all of these forms of energy stream outward from the explosion at the speed of light. Some of this radiation is more dangerous than others, and some of it could have profound effects on our planet's atmosphere and climate. Following close behind the electromagnetic radiation would be something even more mysterious. Neutrinos, those ghostly particles created when protons and electrons are crushed together in the collapsing stellar core, would flood through our solar system. These particles are so weakly interacting with matter that trillions of them are passing through your body right now from various sources, and you can't feel them at all. But a supernova produces so many neutrinos that even these elusive particles could be detected by sensitive instruments on Earth. But perhaps the most dramatic consequence of a nearby supernova would come later, carried by something that moves much more slowly than light. The explosion would create a massive shockwave of hot gas and high-energy particles, expanding outward from the destroyed star at speeds of thousands of miles per second. This supernova remnant, as astronomers call it, would eventually reach our solar system, though it might take thousands of years to make the journey. When this wave of stellar debris finally arrived, it would interact with our sun's solar wind, the stream of charged particles that our star constantly emits into space. The collision between the supernova remnant and our solar system would create a cosmic storm unlike anything in recorded human history. The sky would light up with auroras, visible from every point on Earth, dancing curtains of green, red, and blue light painting the heavens as charged particles interact with our planet's magnetic field. But the effects wouldn't be purely visual. The high-energy radiation from the supernova would begin to interact with Earth's atmosphere in ways that could fundamentally change our planet's chemistry and climate. Our protective ozone layer, which shields us from harmful ultraviolet radiation from the sun, would begin to break down under the assault of cosmic rays and gamma radiation from the stellar explosion. This is where our story takes a more serious turn. The ozone layer isn't just a nice-to-have feature of our atmosphere, it's essential for life as we know it. Without this protective shield, deadly ultraviolet radiation from the sun would reach Earth's surface at levels that could cause mass extinctions. Plants would struggle to survive, the base of the food chain would collapse, and life on land would face unprecedented challenges. Some scientists believe that past supernova explosions may have been responsible for some of the mass extinction events in Earth's history. The Ordovician extinction, which occurred about 450 million years ago and wiped out nearly 85% of marine species, might have been triggered by a gamma-ray burst from a stellar explosion. The evidence is circumstantial, but the timing and the pattern of extinction suggest that something from space delivered a deadly blow to life on our planet. The thought of such violence affecting our world might seem terrifying, but there's something profound we need to understand about the relationship between stellar death and the continuation of life. You see, these explosions aren't just agents of destruction. They're also the universe's way of stirring the pot, mixing and distributing the elements that make complex chemistry and ultimately life possible. When a massive star explodes, it doesn't just release energy and radiation. It creates what astronomers call a supernova remnant, an expanding bubble of superheated gas and dust that can grow to be hundreds of light years across. This cosmic bubble acts like a giant mixing spoon, stirring up the interstellar medium and triggering the formation of new stars and planetary systems. In a very real sense, stellar death gives birth to stellar life, creating the conditions necessary for the next generation of stars to form. But let's return to our scenario. What would actually happen to Earth if a supernova occurred within that critical 50 light-year radius? The answer depends on several factors: How massive was the exploding star? How far away is it exactly? What type of supernova is it? And perhaps most importantly, is the explosion pointed toward us? Not all supernovas are created equal. Some stars explode symmetrically, sending their energy and material outward in all directions like an expanding sphere. Others, particularly the most massive stars, can produce what's called a hypernova or collapser, where the explosion is focused into narrow jets of incredibly energetic particles and radiation. If one of these searchlights happened to be pointed directly at Earth, the consequences would be far more severe than a typical spherical explosion. These focused jets can produce gamma-ray bursts, brief but incredibly intense flashes of the most energetic form of electromagnetic radiation known. A gamma-ray burst pointed at Earth from even 50 light-years away could deliver a radiation dose equivalent to standing next to a nuclear reactor without shielding. The immediate effects would be catastrophic for our ozone layer, but the long-term consequences could reshape life on our planet for millions of years. Let's walk through what would happen day by day, year by year, as the effects of a nearby supernova gradually reached our world. On day 0, the moment of explosion, nothing changes on Earth. The star has died, but its final message hasn't reached us yet. Light from the explosion races toward us through the darkness of space, carrying news of catastrophe at the universe's speed limit. Years pass, decades. Then, depending on the distance, somewhere between 25 and 50 years after the explosion, Earth receives its first notification. A new star appears in our sky, growing brighter with each passing night. Ancient astronomers called these events guest stars or new stars, not knowing they were actually witnessing stellar death from across the galaxy. This new star would be impossible to ignore. Within weeks, it might become the brightest object in the night sky after the moon. Unlike planets or other stars, this beacon would be visible even during the day, a pale point of light that would have medieval populations convinced that the end times had arrived. Modern astronomers, of course, would know exactly what they were looking at, and the implications would send shockwaves through the scientific community. The visible light show would be spectacular, but it would only be the beginning. Following closely behind the optical display would come the invisible forms of radiation that could spell trouble for our planet. X-rays and gamma rays would begin bombarding Earth's upper atmosphere, interacting with nitrogen and oxygen molecules in ways that would start a slow but steady destruction of our protective ozone layer. The process wouldn't be immediate or dramatic. There would be no sudden flash that kills everything on Earth. Instead, the ozone depletion would happen gradually over months and years, like a slow leak in a tire. Atmospheric scientists would watch in fascination and growing concern as their instruments detected the steady decline in ozone concentrations around the globe. As the ozone layer thinned, more and more ultraviolet radiation from our sun would reach Earth's surface. The effects would first become apparent in the ocean, where microscopic plants called phytoplankton form the base of the marine food web. These tiny organisms are extremely sensitive to UV radiation, and their populations would begin to crash as the protective ozone shield weakened above them. The collapse of phytoplankton populations would send ripples up through the entire ocean ecosystem. Fish that depend on these microscopic plants for food would find their food supply dwindling. Larger predators would struggle as their prey became scarce. The ocean, which covers more than 70% of our planet's surface and produces much of the oxygen we breathe, would begin to change in fundamental ways. On land, the story would be similar, but perhaps even more dramatic. Plants, which have evolved over millions of years under the protection of our ozone layer, would suddenly find themselves exposed to levels of UV radiation they were never designed to handle. Forests would begin to brown and die, starting with the most sensitive species and gradually spreading to affect entire ecosystems. Agricultural crops, many of which are particularly vulnerable to UV damage, would face unprecedented challenges. Farmers around the world would watch their yields decline as plants struggled to survive under the harsh radiation. Food shortages would follow, leading to economic and social upheaval on a global scale. But perhaps the most insidious effect would be on DNA itself. Ultraviolet radiation is a powerful mutagen, capable of damaging the genetic code that serves as the instruction manual for all life on Earth. As UV levels increased, mutation rates would soar. Most of these mutations would be harmful or fatal, but some might prove beneficial, accelerating evolution in unpredictable directions. The effects on human health would be profound and immediate. Skin cancer rates would skyrocket as people around the world found themselves exposed to dangerous levels of UV radiation. Eye damage, including cataracts and blindness, would become increasingly common. Even brief exposure to sunlight without protection could result in severe burns and tissue damage. But humans, being the adaptable species we are, would find ways to cope. We would develop better sunscreens, design protective clothing, and modify our daily routines to avoid the most dangerous hours of sunlight. We might even begin to live increasingly indoor lifestyles, venturing outside only when absolutely necessary and only with extensive protection. The supernova's effects wouldn't stop with biological systems. The high-energy particles streaming from the stellar explosion would interact with Earth's magnetic field, creating geomagnetic storms that could disrupt our technological civilization. Satellites would malfunction or fail entirely as they're bombarded by cosmic rays. Power grids would face unprecedented challenges as geomagnetic fluctuations induce dangerous currents in transmission lines. Communication systems, from cell phones to GPS networks, would become unreliable as the ionosphere, the layer of Earth's atmosphere that reflects radio signals, becomes chaotic and unpredictable. Air travel would become hazardous as pilots lose navigation aids and passengers face increased radiation exposure at high altitudes. The aurora displays, those beautiful dancing lights normally confined to polar regions, would become a global phenomenon. Night after night, the sky would light up with brilliant curtains of colored light as charged particles from the supernova remnant interact with our planet's magnetic field. What would normally be considered a stunning natural wonder would become a constant reminder of the cosmic catastrophe affecting our world. Years would pass, and gradually, the most intense effects of the supernova would begin to fade. The ozone layer, given time and reduced radiation bombardment, would slowly begin to recover. Life on Earth, remarkably resilient as it has proven to be through previous mass extinctions, would adapt to the new conditions. But our world would be forever changed. The species that survived would be those best adapted to high UV environments. New evolutionary pressures would drive rapid changes in plant and animal populations. The very trajectory of life on Earth would have been altered by the death of a star dozens of light years away. This scenario while dramatic, helps us understand something profound about our place in the universe. We often think of Earth as an isolated oasis, protected and separate from the violence of space. But the truth is that we're intimately connected to the cosmos around us. The elements in our bodies, the energy that powers our sun, even the conditions that allow life to exist, all trace back to stellar processes that occur throughout our galaxy. The story of a nearby supernova isn't just about destruction and catastrophe. It's about the deep connections that bind us to the universe, the delicate balance that allows life to flourish, and the cosmic processes that continue to shape our world in ways both beautiful and terrifying. As we drift deeper into this cosmic tale, let's explore the more subtle yet equally profound ways a nearby supernova would reshape our understanding of existence itself. Beyond the immediate physical effects, such an event would mark a turning point in human consciousness, a moment when our species would be forced to confront the reality that we truly live in a dynamic, ever-changing universe where even the stars themselves are mortal. The psychological impact on humanity would be immense. For thousands of years, we've looked up at the night sky and seen constancy. The same constellations that guided ancient mariners still wheel overhead today. The North Star has been a reliable beacon for countless generations. But a nearby supernova would shatter this illusion of cosmic permanence. Suddenly, we would be confronted with undeniable proof that the universe is not the stable, unchanging backdrop we once imagined. Children growing up during such an event would have a fundamentally different relationship with the cosmos than any generation before them. They would know from their earliest memories that stars can die, that space is filled with invisible radiation, that our planet's protective systems can be damaged by events occurring impossibly far away. This knowledge would shape their worldview in ways we can barely imagine. The scientific revolution that would follow would be unprecedented. Suddenly, every aspect of astronomy, atmospheric science, and biology would take on urgent practical importance. Research budgets that might normally face political battles would receive immediate approval as governments around the world recognize the existential nature of the threat. The space program would receive a boost unlike anything since the early days of the Cold War, as humanity scrambled to better understand and perhaps defend against cosmic dangers. But let's pause for a moment and consider something beautiful hidden within this cosmic catastrophe. The very radiation that would pose such a threat to life on Earth would also create some of the most spectacular natural phenomena our planet has ever witnessed. The interaction between high-energy particles from the supernova and our planet's magnetic field would paint the sky with colors and patterns that would make the northern lights seem pale by comparison. Imagine stepping outside on any clear night and seeing the entire sky alive with shimmering curtains of light. Green and blue and red and gold, dancing and swirling in patterns that seem almost alive. These auroras would be visible from every point on Earth, from the equator to the poles, transforming every evening into a cosmic light show of unprecedented beauty. The night sky would become a constant reminder of the stellar explosion that had changed our world. As the supernova remnant continued to expand and interact with the interstellar medium, the display would evolve over years and decades. Some nights, the auroras might be subtle, just a gentle glow on the horizon. Other nights, they might fill the entire sky with brilliant, shifting patterns that would make sleep impossible as people stood transfixed by the celestial dance above their heads. Photographers and artists would find themselves with subject matter unlike anything in human history. The aurora displays would vary not just from night to night, but from hour to hour, as different packets of charged particles arrived from the distant stellar explosion. No two displays would be exactly alike, creating an endless source of wonder and inspiration. But beneath this beauty would lie a sobering reminder of our cosmic vulnerability. The same particles creating these magnificent light shows would be slowly but steadily eroding our planet's protective ozone layer. It would be like watching a beautiful poison slowly take effect, magnificent to behold but ultimately destructive. The timing of such an event would matter enormously. If a nearby supernova had occurred during the age of dinosaurs, life on Earth would have faced the challenge with very different capabilities. Plants and animals that had evolved over millions of years under stable ozone conditions would have had to adapt quickly or face extinction. The fossil record suggests that life has survived such cosmic challenges before, but always at great cost. If the explosion happened in our current era, humanity would bring unique advantages to the survival challenge. Our technology would allow us to monitor the effects in real time, to understand exactly what was happening to our planet's atmosphere and biosphere. We could develop protective measures, create artificial ozone if necessary, and perhaps even find ways to shield the most vulnerable ecosystems. More importantly, we could communicate globally about the crisis, sharing information and coordinating responses in ways that no other species in Earth's history has been able to do. While individual plants and animals would face the harsh reality of increased UV radiation with only their evolved defenses, humans could adapt behaviorally, technologically, and socially. The agricultural challenges alone would drive innovation at an unprecedented pace. Farmers would need to develop new crop varieties capable of surviving under higher UV conditions. Greenhouse agriculture would become not just economically advantageous, but essential for food security. We might see the rapid development of transparent materials that block harmful radiation while allowing photosynthesis to continue. Urban planning would need to adapt as well. Cities would require more covered walkways, underground passages, and buildings designed to provide refuge from dangerous levels of solar radiation. The very architecture of human civilization might evolve to accommodate this new reality, creating enclosed communities that could maintain normal life while the outside world struggled with increased radiation. But perhaps most fascinating would be the biological adaptations that would emerge over longer time scales. Evolution, which normally operates over thousands or millions of years, can accelerate dramatically when faced with strong selective pressure. Species with even slight advantages in UV resistance would find themselves with enormous survival benefits. We might witness the rapid evolution of enhanced DNA repair mechanisms in many species. Plants might develop thicker waxy coatings on their leaves or more effective chemical sunscreens in their tissues. Animals could evolve better UV blocking pigments in their skin or eyes, or behavioral adaptations that minimize their exposure to dangerous radiation. For humans, the evolutionary pressure would be complicated by our technological abilities. While natural selection would favor individuals with better UV resistance, our medical technology would also work to protect those who might otherwise be vulnerable. The result could be a fascinating interplay between biological and technological adaptation. Some regions of Earth would fare better than others during such a cosmic crisis. Areas with naturally higher cloud cover would receive some protection from the increased UV radiation. Underground communities, whether natural cave systems or human-made structures, would become valuable refuges. The polar regions, already adapted to extreme conditions and seasonal variations in sunlight, might prove more resilient than temperate zones. Ocean ecosystems would face particular challenges, as the microscopic organisms at the base of marine food webs are often the most sensitive to radiation damage. But the ocean's depth would provide natural shielding, and life in deeper waters might actually find itself at an advantage as surface ecosystems struggled. The economic implications would be staggering. Industries dependent on outdoor activities, from agriculture to tourism to construction, would face unprecedented challenges. At the same time, entirely new industries would emerge almost overnight. Companies specializing in radiation protection, atmospheric monitoring, and UV-resistant materials would find themselves at the center of the global economy. The insurance industry would face a crisis unlike anything in its history. How do you calculate the risk of radiation when the fundamental assumptions about Earth's environment have suddenly changed? Traditional models based on historical weather patterns and natural disasters would become obsolete virtually overnight. International cooperation would become not just desirable, but essential for survival. No single nation, no matter how technologically advanced, could address all the challenges of a nearby supernova alone. We would need global coordination on atmospheric monitoring, shared research into protective technologies, and collaborative efforts to maintain food security as agricultural systems worldwide faced unprecedented stress. The event would also force us to confront uncomfortable questions about resource allocation and global equity. Would protective technologies be available to everyone, or would they become another source of inequality between rich and poor nations? How would we prioritize which ecosystems to protect when we couldn't save them all? Religious and philosophical communities would grapple with the theological implications of such violence affecting our world. Some might see it as divine judgment, others as a test of human resilience and cooperation. The event would certainly challenge any worldview that sees Earth as specially protected or separate from the dangers of the wider universe. Scientific understanding would advance by leaps and bounds as researchers suddenly had a real-world laboratory for studying the effects of cosmic radiation on planetary atmospheres. The data gathered during such an event would revolutionize our understanding of astrobiology, atmospheric chemistry, and the conditions necessary for life to survive cosmic catastrophes. Perhaps most importantly, the experience would fundamentally change how we think about our future as a species. No longer could we assume that Earth would always provide a stable, hospitable environment for human civilization. The reality of cosmic threats would drive serious consideration of space colonization, not as an exciting adventure, but as a necessary insurance policy for human survival. The development of off-world colonies would take on urgent importance as we realize that keeping all of humanity on a single planet makes us vulnerable to catastrophes beyond our control. Mars missions, moon bases, and space habitats would transition from science fiction dreams to practical necessities for species survival. But even as we planned for expansion into space, we would also develop a deeper appreciation for the remarkable planet we call home. The experience of watching Earth's protective systems come under assault would highlight just how perfectly balanced and precious our biosphere really is. We might emerge from such a crisis with a renewed commitment to protecting and preserving the natural systems that make life possible. The story of a nearby supernova would ultimately be a story about resilience, adaptation, and the incredible tenacity of life itself. While such an event would certainly cause tremendous hardship and loss, it would also demonstrate the remarkable ability of living systems to survive, adapt, and eventually thrive under even the most challenging conditions. Throughout Earth's history, life has survived ice ages, asteroid impacts, massive volcanic eruptions, and countless other catastrophes. Each time, the survivors have gone on to diversify and flourish in ways that filled the ecological niches left empty by extinction. A nearby supernova would be another chapter in this ongoing story of survival and renewal. And perhaps, in the end, that's the most profound lesson we can take from contemplating such cosmic violence. The universe may be vast and dangerous, filled with forces that can reshape entire worlds in moments. But life, in all its forms, has proven to be remarkably persistent and creative in finding ways to continue existing and evolving, even under the most extreme circumstances. As you settle deeper into contemplation of these cosmic possibilities, remember that this story of stellar death and planetary challenge is also a story about the deep connections that bind us to the universe around us. The elements forged in ancient supernova explosions flow through our veins. The energy that powers our thoughts and dreams ultimately traces back to nuclear fusion in stellar cores. We are not separate from the cosmos, but part of its ongoing evolution. Participants in a story that stretches from the birth of the first stars to whatever future awaits us among the galaxies. The question of what would happen if a star exploded near Earth isn't just an academic exercise in cosmic catastrophe. It's a meditation on our place in the universe, our responsibilities to each other and to the biosphere that sustains us, and the remarkable journey of consciousness that has brought us to the point where we can contemplate our own cosmic context. The knowledge that our planet exists within this cosmic shooting gallery would fundamentally reshape human priorities in ways both practical and profound. Suddenly, the ancient philosophical question of our place in the universe would take on immediate, practical importance. We would be forced to acknowledge that Earth is not a protected sanctuary, but a small world traveling through a galaxy filled with stellar time bombs, any one of which could dramatically alter the trajectory of life itself. Consider how this awareness would change our approach to scientific research and education. Astronomy would shift from being a purely academic pursuit to an essential survival skill. Every major university would establish departments dedicated to stellar evolution and supernova prediction. We would develop increasingly sophisticated methods for monitoring nearby stars, watching for the telltale signs that indicate a massive star is approaching the end of its life. The signs are subtle but detectable. A star preparing for its final explosion might begin to show irregular brightness variations as its internal structure becomes unstable. Its color might shift as the surface temperature changes. The star might begin to shed mass more rapidly, creating expanding shells of gas and dust around itself. With enough warning, humanity might have decades or even centuries to prepare for the inevitable catastrophe. But preparation for such an event would require unprecedented global cooperation and long-term thinking. How do you plan for a disaster that might not occur for 100 years? How do you maintain funding and political support for protective measures when the threat exists only as calculations on computer screens and theoretical models in scientific papers? The challenge would be similar to climate change but compressed into a much more urgent time frame. Unlike the gradual warming of our planet, the effects of a nearby supernova would be immediately apparent and impossible to deny. There would be no debate about whether the threat was real when a new star suddenly blazed forth in the night sky, growing brighter with each passing hour. The first months after such a stellar explosion would be crucial for humanity's response. Scientists around the world would work frantically to model the incoming radiation and predict its effects on Earth's atmosphere. Computer simulations would run around the clock, calculating the timeline of ozone depletion and the resulting increase in surface UV radiation. Meanwhile, governments would face the enormous challenge of preparing their populations for a new reality. Public health officials would need to develop guidelines for safe exposure to sunlight. Agricultural departments would work with farmers to identify crop varieties that might survive under higher radiation conditions. Urban planners would begin designing modifications to cities that could provide better protection for human populations. The economic disruption would begin even before the most dangerous radiation reached Earth. Stock markets would plunge as investors grappled with the implications of a fundamentally changed world. Industries dependent on outdoor activities would face immediate uncertainty. Tourism to sunny destinations would collapse as travelers reconsidered the wisdom of increased sun exposure. At the same time, entirely new markets would emerge almost overnight. Companies developing UV protective materials would see unprecedented demand. Manufacturers of indoor growing systems would struggle to keep up with orders from farmers preparing for agricultural challenges. The space industry would receive a massive influx of investment as the need for off-world colonies became undeniably urgent. The social and cultural effects would be equally dramatic. Religious communities would grapple with the theological implications of catastrophe. Some might interpret the stellar explosion as divine intervention or judgment. Others would see it as a test of human resilience and cooperation. New spiritual movements might emerge, focused on humanity's relationship with the broader cosmos and our responsibilities as conscious beings in a dynamic universe. Educational systems would need to adapt rapidly to prepare the next generation for life in a world with higher background radiation. Children would learn about ozone chemistry and UV protection alongside traditional subjects like mathematics and literature. School schedules might be modified to minimize outdoor activities during peak radiation hours. Playground equipment would need to be redesigned or covered to provide adequate protection. The arts would find new inspiration in humanity's cosmic predicament. Musicians would compose symphonies inspired by stellar death and rebirth. Painters would capture the beauty and terror of aurora displays that filled the entire sky. Writers would explore themes of survival, adaptation, and humanity's place in an indifferent universe. The very vocabulary of human culture would expand to include concepts and concerns that previous generations never needed to consider. Architecture would evolve in response to the new radiation environment. Buildings would incorporate more sophisticated shielding materials. Windows might be treated with special coatings that block harmful UV while allowing visible light to pass through. underground spaces would become more valuable and desirable. The design of homes, offices, and public spaces would all need to account for the reality of increased cosmic radiation. Transportation systems would face unique challenges. Airline flights would need to be modified to provide better radiation protection for passengers and crew. Routes might be changed to minimize exposure time at high altitudes, where the atmosphere provides less shielding. Spacecraft design would benefit from the urgent need to understand radiation protection, accelerating developments that might otherwise take decades to achieve. The medical profession would find itself at the forefront of humanity's adaptation to cosmic change. Doctors would need to become experts in radiation-related health effects. New treatments would be developed for radiation exposure and UV damage. Preventive medicine would take on unprecedented importance as the focus shifted from treating disease to protecting healthy populations from environmental threats. Hospitals would need to prepare for waves of patients suffering from radiation-related illnesses. Cancer treatment centers would face enormous demand as skin cancer rates soared. Eye care specialists would see increasing numbers of patients with cataracts and other radiation-induced vision problems. The entire healthcare system would need to adapt to serve a population living under fundamentally different environmental conditions. Agricultural science would undergo a revolution as researchers raced to develop crops capable of surviving under higher UV conditions. Traditional farming methods, developed over thousands of years under stable ozone conditions, would suddenly become inadequate. Farmers would need to learn new techniques for protecting their crops from radiation damage while maintaining productivity to feed a world facing food security challenges. Greenhouse agriculture would expand rapidly as growers sought to protect their crops from increased UV radiation. But even greenhouse operations would face new challenges as the materials used in construction would need to provide better filtration of harmful radiation. The entire agricultural supply chain would need to adapt to the new reality of farming under cosmic threat. Ocean ecosystems would provide a fascinating natural laboratory for studying life's adaptation to increased radiation. Marine biologists would observe in real time how ocean food webs respond to the collapse of UV-sensitive species at the base of the food chain. Some organisms might prove surprisingly resilient, while others would face rapid extinction. The resulting ecological reorganization would provide insights into how life adapts to cosmic catastrophes. Fishing industries would face enormous uncertainty as marine ecosystems reorganize themselves. Some fish populations might crash as their food sources disappeared. Others might thrive in the changed conditions, leading to shifts in which species were commercially valuable. Coastal communities dependent on fishing would need to adapt rapidly to changing ocean conditions. The psychological toll on humanity would be immense, but also potentially transformative. The knowledge that our planet exists at the mercy of cosmic forces beyond our control would force a collective reckoning with mortality and meaning. Some individuals might succumb to despair or nihilism when confronted with the vastness and indifference of the universe. Others might find profound purpose in working to protect and preserve life under challenging conditions. Mental health services would face unprecedented demand as populations struggle to cope with existential anxiety on a global scale. But the crisis might also bring out the best in human nature, fostering cooperation, compassion, and collective problem-solving on a scale never before seen. The shared threat would transcend national, cultural, and ideological boundaries, creating a truly global sense of common purpose. Children born during such a cosmic crisis would grow up with a fundamentally different relationship to the universe than any previous generation. They would know from their earliest memories that the cosmos is dynamic, dangerous, and capable of dramatic change. This knowledge might make them more resilient, more adaptable, and more appreciative of the precious and fragile conditions that allow life to flourish. The educational systems designed for these cosmic children would need to balance practical preparation for life under increased radiation with the broader goals of human development. They would learn not just how to protect themselves from UV damage, but also how to find meaning and joy in a universe that had revealed its capacity for sudden dramatic change. Scientific research would advance at an unprecedented pace as the urgency of understanding cosmic threats drove massive investment in astronomy, atmospheric science, and astrobiology. Telescopes would be built and launched to monitor nearby stars with extraordinary precision. Computer models would be developed to predict the behavior of stellar explosions and their effects on planetary atmospheres. The data gathered during humanity's first experience with a nearby supernova would revolutionize our understanding of how life survives cosmic catastrophes. This knowledge would prove invaluable not just for protecting Earth, but for understanding the conditions necessary for life on other worlds throughout the galaxy. Space exploration would receive an enormous boost as the need for backup colonies became undeniably urgent. Mars missions would transition from scientific expeditions to desperate attempts to establish human settlements beyond Earth's atmosphere. The Moon would be developed as a staging ground for deeper space exploration and as a refuge for human populations. But even as we planned for expansion beyond Earth, the cosmic crisis would also deepen our appreciation for the remarkable planet we call home. The experience of watching our world's protective systems come under assault would highlight the incredible complexity and delicate balance of the biosphere that sustains us. Environmental protection would take on new urgency and meaning. If cosmic forces could damage our ozone layer and threaten our ecosystems, how much more important would it become to protect the natural systems that had sustained life for billions of years? The supernova crisis might paradoxically lead to a golden age of environmental stewardship, as humanity finally grasped the fragility and preciousness of our planetary home. International cooperation would reach levels never before achieved, as nations realize that cosmic threats transcend political boundaries. The monitoring networks needed to track stellar explosions, and their effects would require global coordination. The research necessary to develop protective technologies would benefit from shared resources and expertise. The challenge of maintaining food security and protecting vulnerable populations would demand unprecedented levels of international collaboration. New international institutions might emerge to coordinate humanity's response to cosmic threats. A global cosmic monitoring agency might be established to track potentially dangerous stars and space weather events. International protocols would be developed for sharing information about incoming radiation and coordinating protective measures. The concept of planetary defense would expand beyond asteroid impacts to include stellar explosions and other cosmic phenomena. The long-term effects of surviving such a cosmic crisis would reshape human civilization in profound ways. We would emerge from the experience with a deeper understanding of our place in the universe and our responsibilities to each other and to the biosphere that sustains us. The knowledge that life is precious and fragile, threatened by forces beyond our control, might inspire greater cooperation, compassion, and wisdom in how we organize our societies. Future generations would look back on the supernova crisis as a turning point in human history, the moment when our species fully grasped the reality of living in a dynamic, dangerous universe. They would inherit technologies, institutions, and ways of thinking developed in response to cosmic threat. Most importantly, they would inherit the knowledge that life is resilient, adaptable, and capable of surviving even the most extreme challenges when conscious beings work together with wisdom, courage, and determination. As we continue our journey through this cosmic catastrophe, we begin to see that the story of a nearby supernova is ultimately a story about transformation, not just the transformation of matter and energy in a dying star, but the transformation of consciousness, society, and life itself in response to cosmic challenge. It's a reminder that we are not passive observers of the universe, but active participants in its ongoing evolution, capable of adapting, learning, and growing even in the face of forces that dwarf our individual existence. The night sky would never look the same after such an experience. Each star would carry the potential for both creation and destruction, beauty and terror. But perhaps that knowledge would make us more grateful for the gentle light of our own sun, more protective of the atmosphere that shields us, and more determined to ensure that the spark of consciousness that allows us to contemplate these cosmic mysteries continues to burn bright, no matter what challenges the universe might send our way. But as the immediate crisis of radiation bombardment began to stabilize and our protective systems adapted, something even more profound would begin to unfold. The supernova's influence wouldn't end with the initial wave of electromagnetic radiation. Hidden within the expanding shell of stellar debris racing toward our solar system would be something that could reshape not just our planet's chemistry, but the very building blocks of future life itself. The supernova remnant, that vast bubble of superheated gas and cosmic debris expanding outward at thousands of miles per second, would carry with it the newly forged elements created in the star's final moments. Gold, platinum, rare earth metals, and dozens of other heavy elements would be distributed throughout our local region of space, seeding the interstellar medium with materials that had never existed in such concentrations before. When this cosmic treasure trove finally reached our solar system, perhaps thousands of years after the initial light display, it would begin to interact with everything in its path. The outer planets would receive the first doses of this enriched material. Jupiter and Saturn, with their powerful magnetic fields and extensive moon systems, would capture significant quantities of the stellar debris in their magnetospheres. Earth's magnetic field would also trap some of these particles, creating a kind of cosmic time capsule in our planet's radiation belts. Future space missions might literally mine these trapped remnants of stellar death, harvesting rare elements that had been forged in temperatures of billions of degrees and pressures that don't exist anywhere else in the universe. The asteroid belt between Mars and Jupiter would become a particularly interesting region during this cosmic event. The supernova remnant would sweep through this collection of rocky debris, coating asteroid surfaces with a thin layer of stellar material. Future mining operations would discover asteroids with compositions unlike anything previously known, containing concentrations of rare elements that would revolutionize technology and industry. But perhaps the most fascinating consequence would be the effect on comets in the outer reaches of our solar system. These ancient balls of ice and rock, some of which haven't changed since the formation of the solar system, would suddenly acquire new surface layers of exotic materials. When these comets eventually fell into the inner solar system and approached the Sun, they would release not just water vapor and dust, but also traces of elements forged in the heart of a dying star. Earth's atmosphere would gradually acquire new isotopic signatures as these enriched particles slowly filtered down through the upper layers of our protective envelope. Atmospheric scientists would detect the chemical fingerprints of stellar nucleosynthesis in our air itself, breathing in atoms that had been created in the final seconds of a massive star's life. The oceans would tell a similar story. Rain carrying traces of supernova debris would gradually alter the chemical composition of seawater. Marine organisms would begin incorporating these new isotopes into their shells and skeletons, creating a permanent geological record of the cosmic catastrophe. Future paleontologists would be able to identify the exact layers in sedimentary rock that corresponded to the supernova event, marked by distinctive chemical signatures unlike anything in Earth's previous history. This gradual enrichment of our planet with stellar debris would have subtle but profound effects on future evolution. New biochemical pathways might become possible as life gained access to elements and isotopes that had previously been vanishingly rare. Some organisms might develop novel enzymes or cellular structures that could only function with these exotic materials. The magnetic field interactions would create some of the most spectacular and long-lasting effects of the supernova. As charged particles from the stellar explosion interacted with Earth's magnetosphere, they would gradually reshape the structure of our planet's magnetic environment. The Van Allen radiation belts would acquire new characteristics, potentially affecting everything from satellite operations to the behavior of migrating animals that navigate using magnetic cues. Auroras would become a permanent feature of Earth's upper atmosphere, no longer confined to polar regions but visible from every point on the planet. The constant influx of charged particles would create a perpetual light show that would transform the night sky into a canvas of shifting colors and patterns. Children born after the supernova would grow up thinking that aurora displays were a normal part of every evening, never knowing that previous generations had considered them rare and special phenomena. The space environment around Earth would become fundamentally different. The increased radiation and particle flux would pose new challenges for spacecraft and satellites, but it would also create opportunities for new technologies. Solar panels might need to be redesigned to cope with higher energy particle bombardment, but they might also become more efficient as the enhanced radiation environment provided additional energy sources. Future space missions would need to account for the changed conditions throughout the solar system. Spacecraft traveling to the outer planets would encounter enhanced radiation fields and altered magnetic environments. Landing on planets and moons would require new shielding technologies and different mission planning approaches. But these challenges would also drive innovation in space technology at an unprecedented pace. The psychological and cultural effects of living through such a cosmic transformation would ripple through human society for generations. Art, literature, and music would be profoundly influenced by the shared experience of witnessing stellar death and planetary transformation. New mythologies would emerge, stories that tried to capture the meaning of living through such cosmic violence and beauty. Religious and philosophical traditions would grapple with the implications of having witnessed the universe's capacity for both creation and destruction on such a vast scale. Some might develop new theological frameworks that incorporated the reality of cosmic change and stellar mortality. Others might find renewed appreciation for the stability and protection that Earth had provided throughout human history. The scientific revolution that followed would extend far beyond astronomy and atmospheric science. Biology would be transformed as researchers studied how life adapted to the changed conditions. Chemistry would advance rapidly as scientists worked to understand and utilize the new isotopes and elements that had been delivered by the stellar explosion. Physics would benefit from the natural laboratory that the supernova provided, offering insights into high-energy processes that could never be replicated on Earth. Medical science would make unprecedented advances as doctors learned to treat radiation-related conditions and develop new therapies based on understanding how biological systems cope with cosmic stress. The enhanced background radiation would accelerate certain types of medical research, providing natural experiments in how living tissue responds to various forms of electromagnetic energy. Agricultural science would undergo a complete revolution as farmers and researchers worked together to develop crops that could thrive under the new conditions. Some plants might actually benefit from the increased radiation, developing enhanced growth rates or improved nutritional content. Others would need genetic modification or selective breeding to survive in the changed environment. The economic implications would continue to unfold for decades after the initial crisis. New industries would emerge around radiation protection, atmospheric monitoring, and the processing of supernova-delivered materials. Traditional industries would need to adapt their methods and technologies to cope with the altered environment. The global economy would restructure itself around the new realities of life in a post-supernova world. International relations would be permanently altered by the shared experience of cosmic crisis. Nations that had worked together to survive the radiation bombardment would forge new alliances and cooperative frameworks. The concept of planetary defense would expand to include not just protection from asteroids and comets, but also preparation for future stellar explosions and other cosmic threats. Educational systems would evolve to prepare new generations for life in a universe that had revealed its dynamic and dangerous nature. Children would learn about stellar evolution and cosmic radiation alongside traditional subjects. University curricula would expand to include new fields of study that combined astronomy, atmospheric science, biology, and engineering in ways that had never been necessary before. The long-term effects on human evolution would be subtle but significant. Populations living in areas with higher background radiation might gradually develop enhanced DNA repair mechanisms or better cellular protection against radiation damage. The selective pressure wouldn't be as dramatic as that faced by other species, thanks to human technology and medicine, but it would still influence the genetic future of our species. Space colonization efforts would receive unprecedented support and funding as the reality of cosmic threats became undeniable. Mars colonies would be established not as scientific outposts, but as essential backup locations for human civilization. The Moon would be developed as a stepping stone to deeper space exploration, and as a protected environment where critical human knowledge and culture could be preserved. The development of these off-world colonies would be accelerated by the technologies developed in response to the supernova crisis. Radiation shielding, closed-loop life support systems, and methods for growing food in protected environments would all find applications in space settlements. The experience of protecting Earth's population from cosmic radiation would provide valuable lessons for protecting space colonists from the harsh environment beyond our atmosphere. But even as humanity expanded into space, the supernova crisis would also deepen our appreciation for Earth itself. The experience of watching our planet's protective systems come under assault would highlight the incredible complexity and delicate balance that makes our world habitable. Environmental protection would take on new meaning when viewed in the context of cosmic threats that could damage or destroy the natural systems that sustain life. Climate science would benefit enormously from the natural experiment provided by the supernova's effects on Earth's atmosphere. Researchers would gain unprecedented insights into how atmospheric chemistry responds to external forcing, information that would prove valuable for understanding and addressing human-caused climate change. The crisis would provide a unique opportunity to study planetary atmospheres under extreme conditions. The supernova's effects would also influence how we think about the search for life on other worlds. The knowledge that stellar explosions could dramatically alter planetary atmospheres and surface conditions would inform our understanding of habitability around other stars. Astrobiologists would develop new models for how life might survive cosmic catastrophes on planets throughout the galaxy. Future telescope projects would be designed not just to study distant galaxies and exoplanets, but also to monitor nearby stars for signs of impending explosion. A global network of automated observatories would keep constant watch on potentially dangerous stellar systems, providing early warning of future cosmic threats. The technology developed for this monitoring would also prove valuable for other areas of astronomy and space science. The social and cultural evolution that would follow such a cosmic crisis would be profound and lasting. Humanity would emerge from the experience with a fundamentally different relationship to the universe around us. We would understand ourselves not as separate from the cosmos, but as participants in its ongoing evolution, subject to its rhythms of creation and destruction. New forms of art would emerge that try to capture the experience of living through stellar death and planetary transformation. Musicians would compose works inspired by the sounds of cosmic radiation and the visual patterns of aurora displays. Painters would develop new techniques for representing the interplay between beauty and terror that characterizes cosmic phenomena. Writers would explore themes of survival, adaptation, and the meaning of consciousness in a universe capable of such dramatic change. The languages of the world would evolve to include new concepts and vocabulary needed to describe the post-supernova environment. Terms related to cosmic radiation, atmospheric chemistry, and stellar evolution would become part of everyday speech. Children would grow up with words in their vocabulary that previous generations had never needed to learn. Philosophy would grapple with the implications of having witnessed cosmic violence on such a scale. Questions about the meaning of existence, the nature of consciousness, and humanity's place in the universe would take on new urgency and practical importance. New schools of thought would emerge that tried to reconcile the reality of cosmic threat with the human need for meaning and purpose. The legal systems of the world would need to evolve to address the new realities of life in a post-supernova environment. Laws would be developed to govern the use of space-based resources delivered by the stellar explosion. International treaties would be negotiated to ensure fair distribution of the benefits and burdens of cosmic change. New concepts of planetary stewardship would be incorporated into legal frameworks around the world. Insurance industries would face the challenge of calculating risks in a fundamentally altered environment. How do you price policies when the basic assumptions about planetary conditions have changed? New types of coverage would need to be developed for cosmic radiation exposure, atmospheric changes, and space weather events. The entire concept of actuarial science would need to be reconsidered in light of cosmic uncertainties. The media would play a crucial role in helping societies understand and adapt to the cosmic crisis. New forms of journalism would emerge that specialized in translating complex scientific concepts into information that could guide practical decision-making. Documentary filmmakers would find unprecedented subject matter in the story of humanity's response to stellar explosion. News organizations would need to develop expertise in cosmic phenomena that had previously been of purely academic interest. As the decades passed and the most acute effects of the supernova began to stabilize, humanity would gradually adapt to the new cosmic environment. The enhanced aurora displays would become a normal part of the night sky, no longer a source of wonder and fear, but simply another aspect of the natural world. Children would grow up thinking that the brilliant colors dancing across the heavens were as ordinary as clouds or rainbows. The technologies developed in response to the crisis would find applications in countless areas of human life. Better understanding of radiation effects would lead to advances in medical treatments and cancer therapy. Improved atmospheric monitoring would benefit weather forecasting and climate science. Enhanced materials science would produce stronger, lighter, and more durable products for countless industries. But perhaps the most important legacy of the supernova crisis would be the knowledge that humanity could survive and even thrive when faced with cosmic challenges beyond our control. The experience would demonstrate the power of global cooperation, scientific understanding, and human adaptability. It would show that consciousness and intelligence, working together with wisdom and determination, could find ways to preserve and protect life, even when the universe itself seemed hostile. The story of surviving a nearby supernova would become part of human cultural DNA, passed down through generations, as both a cautionary tale and an inspiring example of what our species could accomplish when faced with existential challenge. It would remind future generations that the universe is vast, dangerous, and beautiful, but that conscious beings armed with knowledge, technology, and cooperation can find ways to not just survive, but flourish even in the face of cosmic catastrophe. And in the quiet moments when people looked up at the star-filled sky, now permanently painted with the gentle glow of auroras, born from stellar death, they would remember that they were part of something far greater than themselves. They would understand that the elements in their bodies, the air they breathed, and the very conditions that allowed life to exist, had all been shaped by the violent beauty of stellar evolution. They would know themselves to be not victims of cosmic violence, but participants in the universe's ongoing journey of transformation, destruction, and renewal. The supernova would fade from the night sky eventually, its brilliant light dimming as the expanding shell of debris grew thinner and cooler. But its effects would remain woven into the fabric of Earth's atmosphere, the chemistry of its oceans, and the consciousness of the beings who had witnessed its cosmic drama. The star's death would become part of our planet's story, another chapter in the long history of how cosmic forces shape the evolution of worlds and the life they harbour. In contemplating such cosmic possibilities, we touch something profound about the nature of existence itself. We begin to understand that we are temporary arrangements of stellar debris, conscious patterns in the cosmic flow that have learned to contemplate our own origins and destiny. The universe may be vast and dangerous, filled with forces that can reshape worlds in moments. But it has also given rise to consciousness, to beings capable of understanding and finding meaning in even the most extreme cosmic events. As we drift deeper into this cosmic contemplation, let's explore something that might seem paradoxical about stellar explosions. While we've been focusing on the destructive potential of a nearby supernova, these same cosmic catastrophes are actually responsible for making life possible in the first place. The very atoms that form your body, the oxygen you're breathing right now, the calcium in your bones, the iron in your blood, all of these elements were forged in the nuclear furnaces of dying stars and scattered across the galaxy by supernova explosions. This creates a beautiful and haunting irony. The same type of cosmic event that could threaten our civilization is also what made our existence possible. Every supernova that has occurred in our galaxy's history has contributed to the gradual enrichment of space with heavier elements, slowly building up the cosmic inventory of materials necessary for rocky planets and complex chemistry. When our solar system formed 4.6 billion years ago, it inherited this legacy of stellar death. The disk of gas and dust that would eventually coalesce into the sun and planets was already enriched with elements from countless previous supernovas. Without this cosmic inheritance, Earth would be a very different world, composed primarily of hydrogen and helium, with none of the heavier elements that make complex molecules and life possible. But let's return to our scenario and explore what would happen to Earth's climate systems during and after a nearby stellar explosion. The disruption to our ozone layer would trigger a cascade of atmospheric changes that would reshape weather patterns around the globe. The increased UV radiation reaching the surface would alter the chemistry of the lower atmosphere in subtle but significant ways. Photochemical reactions that normally occur only in the upper atmosphere would begin happening closer to the ground as higher energy radiation penetrated deeper into our atmospheric layers. This would create new types of air pollution and atmospheric chemistry that our weather prediction models had never needed to account for. Meteorologists would find themselves working in uncharted territory as the basic assumptions underlying climate science suddenly changed. The effects on cloud formation would be particularly interesting. Increased ionization in the atmosphere from cosmic ray bombardment could alter the nucleation processes that form clouds. Some regions might see increased cloud cover as particles from the supernova remnant provided new condensation nuclei. Other areas might experience clearer skies as changed atmospheric chemistry disrupted normal cloud formation patterns. Ocean currents, those vast rivers of water that help regulate global climate, would face their own disruptions. The collapse of marine ecosystems at the base of the food web would alter the biological processes that influence ocean chemistry. Dead zones might expand as ecosystems struggle to maintain the delicate balance of nutrients and oxygen that supports marine life. The thermohaline circulation, the global conveyor belt of deep ocean currents driven by temperature and salinity differences, could face significant disruption. Changes in surface temperatures due to altered cloud cover, combined with shifts in precipitation patterns, might alter the density gradients that drive these massive current systems. The consequences could include regional climate changes that persist for decades or centuries after the initial supernova event. Ice sheets and glaciers would respond to the changing climate in complex ways. Some regions might see accelerated melting due to increased surface radiation and altered atmospheric circulation patterns. Others might experience enhanced snowfall as changed weather patterns brought more moisture to polar regions. The net effect on global sea level would depend on the balance between these competing processes. The carbon cycle, that intricate dance of carbon dioxide exchange between the atmosphere, oceans, and biosphere, would face unprecedented disruption. Plants struggling with increased UV radiation would be less efficient at removing carbon dioxide from the atmosphere through photosynthesis. At the same time, stressed ecosystems might release stored carbon as vegetation died and decomposed under the harsh radiation. Soil microbiology would undergo dramatic changes as the microscopic organisms that drive nutrient cycling adapted to higher radiation levels. Some bacteria and fungi might prove surprisingly resilient to cosmic radiation, while others would face population crashes. The resulting shifts in soil chemistry could affect agriculture for generations, long after the most intense radiation had faded. Permafrost regions in the Arctic would face a double challenge. Not only would they experience the same radiation stress as other ecosystems, but the altered atmospheric circulation patterns might also change temperature and precipitation in polar regions. Thawing permafrost could release massive quantities of stored carbon and methane, potentially amplifying climate changes triggered by the supernova. The hydrological cycle, the constant movement of water between oceans, atmosphere, and land, would be reshaped by the cosmic crisis. Changed evaporation rates due to altered surface radiation combined with shifts in atmospheric circulation would create new precipitation patterns around the globe. Some regions might face severe droughts, while others experienced unprecedented flooding. Desert ecosystems, already adapted to harsh radiation conditions, might prove surprisingly resilient to the cosmic onslaught. Plants and animals in arid regions often already possess biological mechanisms for dealing with high UV exposure and limited water availability. These desert-adapted species might find themselves at a sudden advantage, as other ecosystems struggled with the new environmental conditions. Coral reefs, those underwater rainforests that support an extraordinary diversity of marine life, would face a particularly difficult challenge. Already stressed by ocean acidification and warming temperatures, these delicate ecosystems would struggle to cope with the additional burden of increased UV radiation penetrating the ocean's surface. Many reef systems might experience mass bleaching events as the symbiotic algae that provide corals with energy became unable to function under the harsh radiation. Mountain ecosystems would create fascinating natural laboratories for studying how elevation affects exposure to cosmic radiation. The thin atmosphere at high altitudes would provide less protection from the supernova's emissions, creating steep gradients of radiation exposure over relatively short distances. Plants and animals at different elevations would face very different survival challenges, potentially leading to rapid evolutionary changes in mountain species. Migratory animals would face unique difficulties as the cosmic crisis disrupted the environmental cues they rely on for navigation and timing. Birds that use magnetic fields for navigation might find their internal compasses confused by the enhanced geomagnetic activity. Species that time their migrations based on seasonal changes in daylight might struggle as altered atmospheric conditions change the quality and quantity of light reaching different regions. Pollinating insects, already under stress from habitat loss and pesticide use, would face additional challenges from increased UV radiation. Many pollinators are particularly sensitive to changes in light quality and atmospheric chemistry. The disruption of pollination networks could have cascading effects throughout terrestrial ecosystems, affecting plant reproduction and the animals that depend on those plants for food. Nocturnal animals would find their nighttime world transformed by the perpetual aurora displays. Species adapted to darkness might struggle with the constant glow in the sky, while others might adapt to take advantage of the enhanced nighttime illumination. Predator-prey relationships that had evolved under stable lighting conditions would need to adjust to the new cosmic light show. The psychological effects on wildlife would be subtle but significant. Many animals have circadian rhythms that are sensitive to light levels and electromagnetic fields. The constant aurora displays and enhanced geomagnetic activity might disrupt sleep patterns, breeding cycles, and feeding behaviors in ways that would take years for scientists to fully understand. Human settlements would need to adapt their infrastructure to cope with the enhanced space weather environment. Power grids would require better protection against geomagnetic storms that could induce dangerous currents in transmission lines. Communication systems would need redundancy and shielding to maintain connectivity during periods of intense electromagnetic activity. Water treatment facilities would face new challenges as the chemical composition of precipitation changed due to altered atmospheric chemistry. Filtration and purification systems would need to be modified to remove new types of contaminants that had never been present in significant quantities before the supernova. Food production systems would undergo revolutionary changes as agriculture adapted to the new radiation environment. Greenhouse farming would expand rapidly, but even protected growing environments would need new materials and designs to filter out harmful radiation while allowing beneficial light to reach plants. Hydroponic and aeroponic systems might become essential technologies for maintaining food security. Urban planning would evolve to provide better protection for human populations. Cities might develop networks of underground passages and enclosed walkways that would allow people to move around while minimizing exposure to dangerous radiation. Building codes would be updated to require better UV protection in windows and roofing materials. The fashion industry would face an unexpected boom as clothing designed for radiation protection became not just practical, but essential. New fabrics incorporating UV-blocking materials would be developed. Traditional clothing styles would evolve to provide better coverage while remaining comfortable and attractive. Sun protection would become a primary consideration in all clothing design. Educational institutions would need to modify their facilities and schedules to protect students and staff from increased radiation exposure. Outdoor sports and activities would require new safety protocols. School buildings would need upgraded windows and ventilation systems to maintain safe indoor environments while still providing natural lighting. Transportation systems would adapt to the new environmental conditions. Vehicles might incorporate better UV filtering glass and radiation shielding for passengers. Public transportation would become increasingly important as people sought to minimize their time outdoors during peak radiation hours. The tourism industry would face fundamental changes as traditional sun and beach destinations became potentially hazardous. New forms of tourism might emerge around viewing the spectacular aurora displays that would become visible worldwide. Adventure tourism might shift toward underground experiences and protected environments. Healthcare systems would need to expand their capacity for treating radiation-related conditions, while also developing new preventive care protocols. Regular health screenings for radiation exposure would become routine. Medical education would need to include extensive training in radiation medicine that had previously been specialized knowledge. Insurance companies would struggle to calculate risks in the fundamentally altered environment. Life, health, and property insurance would all need to be restructured to account for cosmic radiation exposure and related health effects. New types of coverage would emerge for space weather damage and atmospheric disruption. The entertainment industry would find inspiration in humanity's cosmic predicament. Movies, television shows, and video games would explore themes of survival and adaptation in a post-supernova world. The aurora displays would provide spectacular backdrops for artistic productions. New forms of entertainment might emerge that celebrated humanity's resilience in the face of cosmic challenges. Scientific research would experience a golden age as the supernova provided unprecedented opportunities to study atmospheric physics, radiation biology, and planetary science. Universities would establish new interdisciplinary programs combining astronomy, atmospheric science, and environmental health. Research funding would flow toward understanding and mitigating cosmic threats. International space agencies would coordinate unprecedented missions to study the supernova remnant and its effects throughout the solar system. Spacecraft would be designed to sample the expanding shell of stellar debris and analyze its composition. These missions would provide invaluable data about stellar nucleosynthesis and the distribution of heavy elements in space. The experience would fundamentally change how humanity thinks about planetary defense and survival. No longer would we consider only asteroid impacts and comet collisions as cosmic threats. The reality of stellar explosions would drive new approaches to monitoring nearby stars and preparing for future cosmic catastrophes. Long-term planning would take on new importance as societies grappled with threats that operated on timescales far longer than typical political or economic cycles. Governments would need to develop new institutions capable of maintaining vigilance and preparation across multiple generations. The concept of intergenerational responsibility would gain practical urgency. As we continue this cosmic journey, we begin to see that the story of a nearby supernova is ultimately about transformation and adaptation. It's about how life, consciousness, and civilization can persist and even thrive when faced with challenges that seem to dwarf our individual existence. The universe may be vast and dangerous, but it has also given rise to intelligence, capable of understanding and preparing for cosmic threats. The knowledge that such events are possible, and indeed inevitable over cosmic timescales, might paradoxically make us more grateful for the stable conditions that have allowed our civilization to flourish. It would remind us that the gentle light of our sun, the protective embrace of our atmosphere, and the delicate balance of our biosphere are not permanent fixtures, but temporary gifts that deserve our protection and appreciation. In the quiet moments when people looked up at the aurora-painted sky, they would see not just the beautiful aftermath of stellar death, but also a reminder of the deep connections that bind us to the cosmos. They would understand that we are not separate from the universe, but part of its ongoing story of creation, destruction, and renewal. And in that understanding, they might find not fear, but wonder at the privilege of being conscious participants in such a magnificent cosmic dance. The immediate aftermath of surviving such a cosmic ordeal would reveal something profound about the nature of consciousness itself. As communities around the world work to rebuild and adapt, a new form of collective awareness would emerge. Humanity would have shared an experience that no other generation in recorded history had faced. We would carry within our cultural memory the knowledge of what it means to witness stellar death and planetary transformation on such an intimate scale. Children born during the peak radiation years would grow up with abilities that previous generations never possessed. Their eyes, adapted from birth to the enhanced electromagnetic environment, might be capable of perceiving subtle variations in the aurora displays that older observers could never detect. Their nervous systems, developed under constant low-level cosmic radiation, might process information in ways that neuroscientists are only beginning to understand. These cosmic children would speak of colors in the night sky that had no names in any human language. They would describe patterns in the dancing lights that seemed to follow rhythms and melodies invisible to those who remembered the old, quiet skies. Their art would incorporate visual elements that reflected their unique perceptual abilities, creating new forms of expression that captured aspects of the post-supernova world that words alone could never convey. The generation gap would take on entirely new meaning, as those who remembered the pre-supernova world struggled to relate to young people who had never known a sky without constant aurora displays. Grandparents would tell stories of nights when the stars were clearly visible, when the aurora borealis was confined to polar regions, when going outside during daylight hours required no special protection. To the cosmic children, these tales would seem as fantastical as fairy stories. Educational systems would evolve specialized curricula for these enhanced young minds. Teachers would discover that students who had developed under cosmic radiation showed different learning patterns, different ways of processing spatial and temporal information. Some might demonstrate unusual abilities in mathematics and physics, as if constant exposure to cosmic phenomena had fine-tuned their brains for understanding complex natural patterns. The legal systems of the world would grapple with unprecedented questions about the rights and responsibilities of beings whose fundamental biology had been altered by cosmic forces. Were the cosmic children a new subspecies of humanity? Did they have different needs that society was obligated to meet? How would inheritance laws apply to beings whose lifespans and capabilities might differ significantly from their parents? Medical research would reveal fascinating adaptations in the post-supernova population. DNA repair mechanisms would show enhanced efficiency compared to pre-crisis baseline measurements. Cellular structures would demonstrate improved resistance to radiation damage. Some individuals might develop novel biochemical pathways that allowed them to process and even benefit from certain types of electromagnetic radiation. The enhanced magnetic sensitivity that some people developed would create new professions and capabilities. Human magnetometers would become valuable for navigation and geological survey work. Some individuals might develop an intuitive understanding of space weather patterns, able to predict geomagnetic storms hours or days before instruments detected them. Agricultural systems would stabilize around new equilibrium states as crops and livestock adapted to the altered environment. Plant breeders would discover varieties that not only survived under enhanced radiation, but actually thrived, producing higher yields and more nutritious food than their pre-supernova ancestors. Some crops might develop the ability to photosynthesize, using parts of the electromagnetic spectrum that had previously been harmful. Animal populations would show remarkable evolutionary flexibility as species adapted to the new conditions over surprisingly short timescales. Birds might develop enhanced magnetic navigation abilities as they learn to interpret the more complex geomagnetic environment. Marine organisms could evolve new biochemical pathways that allowed them to process the exotic isotopes that continue to filter into ocean ecosystems. The space industry would experience unprecedented growth as the cosmic crisis made clear the importance of expanding human presence beyond Earth. Space habitats would be designed not as scientific outposts, but as genuine alternative homes for human civilization. The technologies developed for protecting Earth's population from cosmic radiation would find immediate application in creating safe living spaces throughout the solar system. Mars colonies would benefit enormously from the radiation protection technologies developed during the supernova crisis. Colonists would arrive on the red planet equipped with sophisticated life support systems and protective materials that might have taken decades longer to develop without the urgent need created by the stellar explosion. The harsh Martian environment would seem almost benign compared to what Earth had endured. Lunar settlements would serve as stepping stones to deeper space exploration and as archives for human knowledge and culture. Underground cities excavated in the Moon's subsurface would provide safe havens where critical information could be preserved against future cosmic catastrophes. The Moon's lack of atmosphere, once seen as a disadvantage, would become an asset for astronomical observations and early warning systems. The asteroid belt would be transformed into a vast mining and manufacturing zone, as humanity learned to harvest the exotic materials delivered by the supernova. Rare elements that had been impossibly expensive before the stellar explosion would become available in quantities that enabled entirely new technologies. Spacecraft construction would advance by centuries in mere decades as designers gained access to materials with properties that had previously existed only in theoretical calculations. Communication networks would evolve to operate reliably in the enhanced electromagnetic environment. Quantum communication systems, once purely experimental, would become essential infrastructure as traditional radio and satellite communications proved vulnerable to space weather effects. The development of these quantum networks would inadvertently lay the groundwork for computational capabilities that would revolutionize every aspect of human civilization. Energy production would undergo fundamental changes as engineers learned to harness the constant influx of cosmic radiation. Solar panel efficiency would improve dramatically as designers learned to capture and convert the broader spectrum of electromagnetic energy now reaching Earth's surface. New forms of power generation might emerge that could tap directly into the enhanced geomagnetic fields created by the ongoing interaction with the supernova remnant. Transportation systems would adapt to the new environment in unexpected ways. Vehicles might incorporate electromagnetic field manipulators that could interact with the enhanced aurora phenomena for navigation and even propulsion. High-altitude aircraft could be designed to harvest energy from the constant particle bombardment in the upper atmosphere, reducing their dependence on traditional fuel sources. The entertainment industry would create entirely new art forms around the spectacular visual displays that had become part of daily life. Aurora orchestras would compose musical pieces that synchronized with the shifting patterns of light in the sky. Interactive entertainment systems would allow users to influence and direct the electromagnetic phenomena, creating personalized light shows that responded to human emotion and intention. Architecture would evolve beyond mere radiation protection to incorporate aesthetic elements that celebrated the new cosmic environment. Buildings would be designed with transparent aluminum and specialized glass that could filter harmful radiation while creating beautiful prismatic effects with the enhanced atmospheric phenomena. Interior spaces would feature electromagnetic field manipulators that could create miniature aurora displays for decoration and mood enhancement. Fashion would embrace the new reality with clothing that could interact with the electromagnetic environment. Garments might incorporate conductive fibers that could create subtle visual effects when exposed to cosmic radiation. Jewelry could be designed to fluoresce in response to specific types of electromagnetic energy, creating personal aurora displays that reflected the wearer's location and the current space weather conditions. The culinary arts would adapt to work with food sources that had been fundamentally altered by cosmic radiation. Chefs would discover that some plants developed entirely new flavors and nutritional profiles after exposure to the stellar debris. Molecular gastronomy would advance rapidly as cooks learned to work with exotic isotopes and novel chemical compounds that had been created by the interaction between terrestrial matter and supernova remnants. Scientific research would enter a golden age as the natural laboratory created by the supernova provided unprecedented opportunities to study high-energy physics, atmospheric chemistry, and evolutionary biology. Universities would establish new interdisciplinary departments that combined astronomy, biology, chemistry, and engineering in ways that had never been necessary before. The pace of discovery would accelerate exponentially as researchers gained access to natural phenomena that could never be replicated in terrestrial laboratories. International cooperation would reach levels never before achieved in human history as nations realized that cosmic threats transcended all political boundaries. The monitoring networks needed to track space weather and cosmic debris would require global coordination and resource sharing. New international institutions would emerge to manage the distribution of supernova-delivered resources and coordinate research into cosmic phenomena. Philosophy and religion would grapple with the implications of having witnessed cosmic violence on such a scale, while also experiencing the universe's capacity for renewal and transformation. New spiritual movements might emerge that celebrated the interconnectedness of all matter and energy in the cosmos. Traditional religions would need to incorporate the reality of stellar death and rebirth into their understanding of divine purpose and cosmic meaning. The concept of time itself would take on new significance as humanity learned to think in cosmic rather than human timescales. Long-term planning would extend across multiple centuries as societies prepared for future stellar explosions and other cosmic events. The idea of intergenerational responsibility would gain practical urgency as each generation understood that their actions could affect humanity's ability to survive future cosmic catastrophes. Economic systems would restructure themselves around the reality of cosmic resource delivery and space-based industries. New forms of currency might emerge based on rare elements and exotic materials that could only be obtained from stellar explosions. The concept of scarcity would be redefined as humanity gained access to materials that had previously been impossibly rare, but were now available in cosmic abundance. Legal frameworks would evolve to address ownership and distribution of materials that had literally fallen from the sky. International space law would expand to cover the mining and processing of supernova remnants. New concepts of planetary stewardship would emerge as humanity recognized its responsibility to protect Earth's altered but still precious biosphere. The story of surviving a nearby supernova would become humanity's defining myth, passed down through generations as both cautionary tale and inspiring example of what conscious beings could accomplish when faced with cosmic challenge. It would remind future generations that consciousness and intelligence, working together with wisdom and determination, could find ways to not just survive, but transform even the most extreme cosmic events into opportunities for growth and evolution. As the decades turned to centuries and the most dramatic effects of the supernova faded into the background of a normal existence, humanity would carry forward the profound lessons learned during those transformative years. We would understand ourselves not as separate from the cosmos, but as participants in its ongoing evolution, temporary arrangements of stellar matter that had achieved the remarkable feat of consciousness and the even more remarkable feat of survival in the face of cosmic catastrophe. The night sky, forever changed by dancing lights and enhanced electromagnetic phenomena, would serve as a constant reminder of our cosmic heritage and our cosmic responsibilities. Each aurora display would tell the story of stellar death and renewal, of matter and energy transformed across vast scales of space and time, of conscious beings who had learned to find beauty and meaning even in the universe's most violent expressions. In quiet moments, when people paused to contemplate the lights dancing overhead, they would understand that they were witnessing something far more profound than mere atmospheric phenomena. They would see the ongoing conversation between matter and energy, between creation and destruction, between the vast impersonal forces of the cosmos and the precious flame of consciousness that allows the universe to know and appreciate itself. The supernova's greatest gift would not be the exotic materials it delivered or the technologies it inspired, but the transformation of human consciousness itself. We would emerge from the cosmic crisis with a deeper understanding of our place in the universe, our connections to each other, and our responsibilities as the universe's way of understanding itself. We would carry forward the knowledge that life is both fragile and resilient, threatened by forces beyond our control, yet capable of adaptation and growth beyond our wildest imagination. As we near the end of our cosmic journey through stellar catastrophe, we find ourselves contemplating something that transcends the immediate drama of radiation and atmospheric change. The true legacy of surviving a nearby supernova would be written not just in the altered chemistry of our atmosphere or the enhanced glow of perpetual auroras, but in the fundamental transformation of what it means to be human in a universe that has revealed both its creative power and its capacity for destruction. In the decades following such an event, as societies stabilized and adapted to their new cosmic environment, children would grow up with an intuitive understanding that previous generations had never possessed. They would see connections between earthly phenomena and celestial events that older minds struggled to grasp. When they watched waves crash on a beach, they would understand viscerally that the water had been enriched with elements forged in the heart of a dying star. When they breathed the evening air, they would know that each molecule had been touched by cosmic forces, operating on scales that dwarfed human imagination. These post-supernova generations would develop what we might call cosmic consciousness, a deep awareness of the interconnectedness between terrestrial life and galactic processes. Their scientific intuitions would prove remarkably accurate, as if constant exposure to cosmic phenomena had fine-tuned their ability to perceive patterns in natural systems. Researchers would discover that individuals raised under the enhanced electromagnetic environment showed unusual aptitudes for understanding complex dynamic systems, from weather patterns to ecological relationships to quantum mechanical processes. The educational systems that emerged to serve these cosmically aware students would bear little resemblance to traditional classroom models. Learning would become more experiential, more connected to the direct observation of natural phenomena. Students would study atmospheric chemistry by watching the nightly light displays, learn about electromagnetic fields by observing how aurora patterns responded to solar wind variations, understand evolutionary biology by tracking how species adapted to their altered environment in real time. Art and literature would evolve new forms of expression that captured aspects of post-supernova existence that ordinary language could never convey. Poets would develop vocabularies for describing colors that had no names in any human tongue, the subtle variations in aurora light that spoke to observers with enhanced electromagnetic sensitivity. Musicians would compose pieces that incorporated the natural rhythms of geomagnetic fluctuations, creating harmonies that resonated with the planet's altered electromagnetic field. Visual artists would work with materials that had never existed before the stellar explosion, pigments and minerals that had been forged in the final moments of stellar collapse and delivered across interstellar space. Their creations would literally glow with the remnants of stellar fire, incorporating isotopes that had been created in temperatures exceeding billions of degrees. Gallery visitors would view artworks that were simultaneously beautiful and profound reminders of cosmic violence and renewal. Architecture would transcend mere functional adaptation to radiation protection, evolving into an art form that celebrated humanity's survival and transformation. Buildings would be designed as cosmic cathedrals, structures that could channel and display the electromagnetic phenomena that had become part of daily life. Interior spaces would feature controlled aurora displays, allowing people to experience the beauty of cosmic light in intimate, personal settings. The psychological effects of living through such cosmic drama would ripple through human culture in ways both subtle and profound. Mental health professionals would develop new therapeutic approaches that helped individuals process existential anxiety on a cosmic scale. Support groups would form around the shared experience of witnessing stellar death and planetary transformation. New forms of meditation and mindfulness practice would emerge that incorporated awareness of cosmic connectivity, and the impermanence of all stellar systems. Religious and spiritual traditions would undergo fundamental re-examination as believers grappled with the implications of having witnessed the universe's capacity for both creation and destruction on such an intimate scale. Some faith communities would develop new theological frameworks that celebrated the role of stellar death in creating the conditions for life. Others would find renewed appreciation for the fragility and preciousness of existence in a dynamic, ever-changing cosmos. The space exploration programs that emerge from the cosmic crisis would represent humanity's most ambitious undertaking since the development of agriculture. No longer would space travel be seen as adventurous exploration or scientific research. It would be understood as essential species survival strategy, the necessary next step in human evolution. The technologies developed for protecting Earth's population from cosmic radiation would enable the construction of space habitats that could support large populations indefinitely. Mars would be transformed from a distant red dot in the sky to humanity's second home, a world where the lessons learned during the supernova crisis would find immediate practical application. The colonists who made the journey to the red planet would carry with them not just advanced technology, but also the hard-won wisdom of a species that had learned to survive cosmic catastrophe through cooperation, adaptation, and determination. The asteroid belt would become humanity's industrial heartland, a vast factory complex where the exotic materials delivered by the supernova could be processed and manufactured into technologies that would have seemed like magic to previous generations. Mining operations would harvest not just traditional metals and minerals, but also the rare isotopes and elements that had been created in the stellar explosion and scattered throughout the solar system. Communication networks would evolve beyond anything previously imagined as engineers learned to work with quantum entanglement and electromagnetic phenomena that had been enhanced by the cosmic event. Information could be transmitted instantaneously across interplanetary distances, creating a truly connected solar system civilization. The enhanced geomagnetic environment would enable new forms of data transmission that use the planet's magnetic field itself as a communication medium. Energy production would undergo revolutionary changes as humanity learned to harvest power directly from the cosmic phenomena that surrounded them. The constant aurora displays would become more than beautiful light shows. They would be recognized as vast energy sources that could power entire cities. Geomagnetic generators would tap into the enhanced magnetic field fluctuations, providing clean, renewable energy that was literally powered by the remnants of stellar death. Transportation systems would evolve to work with rather than against the altered electromagnetic environment. Vehicles would use magnetic field interactions for propulsion and navigation, reducing dependence on traditional fuels. High-altitude aircraft would ride the enhanced atmospheric currents created by cosmic particle bombardment, achieving efficiency levels that had been impossible under pre-supernova conditions. The economic systems that emerged would be fundamentally different from anything in human history. Traditional concepts of scarcity would need to be reconsidered when cosmic events could deliver vast quantities of previously rare materials. New forms of currency might be based on energy storage capacity or electromagnetic field manipulation capabilities rather than precious metals or fiat declarations. International relations would be permanently transformed by the shared experience of cosmic crisis. Nations that had worked together to survive the radiation bombardment would forge new forms of cooperation that transcended traditional political boundaries. The concept of planetary citizenship would emerge as people recognized that cosmic threats affected all humanity, regardless of nationality, ethnicity, or ideology. Scientific research would advance at unprecedented rates as the natural laboratory created by the supernova provided opportunities to study phenomena that could never be replicated artificially. Universities would establish new interdisciplinary programs that combined astronomy, biology, chemistry, physics, and engineering in ways that reflected the interconnected nature of cosmic and terrestrial systems. The pace of discovery would accelerate exponentially as researchers gained access to natural experiments operating on scales from quantum to galactic. The long-term effects on human evolution would be subtle but significant. Populations living under enhanced cosmic radiation would gradually develop improved DNA repair mechanisms and cellular protection systems. Some individuals might evolve enhanced sensitivity to electromagnetic fields, becoming living instruments capable of detecting subtle changes in space weather conditions. These adaptations would represent the beginning of humanity's transition from a purely terrestrial species to one adapted for life in a cosmic environment. Agricultural systems would stabilize around new equilibrium states as crops and livestock completed their adaptation to altered environmental conditions. Some plants would develop the ability to use previously harmful radiation for photosynthesis, creating food sources that were more nutritious and productive than their pre-supernova ancestors. Animal populations would show remarkable resilience as species that had seemed threatened by the initial radiation exposure revealed unexpected adaptive capabilities. Medical science would make breakthrough discoveries as researchers studied how biological systems responded to cosmic stress. New treatments would be developed based on understanding how living tissue adapted to enhanced electromagnetic environments. The accelerated mutation rates caused by increased radiation exposure would, paradoxically, lead to advances in genetic therapy and cellular regeneration that might have taken centuries to achieve under normal conditions. The entertainment industry would create entirely new art forms around the spectacular phenomena that had become part of daily life. Interactive experiences would allow participants to influence and direct electromagnetic displays, creating personalized cosmic light shows. Virtual reality systems would enable people to experience simulated journeys through supernova remnants, providing safe ways to explore the cosmic forces that had transformed their world. So tonight, as you rest beneath skies forever changed by stellar fire, remember that you've journeyed through one of the universe's most profound possibilities. We've explored how the death of a single star could reshape our entire world, from the delicate chemistry of our atmosphere to the very consciousness of future generations. The aurora-painted heavens would serve as eternal reminders that we are not separate from the cosmos, but woven into its grand tapestry of creation and destruction. Sweet dreams, fellow cosmic travelers, knowing that even in the face of stellar violence, life finds remarkable ways to adapt, survive, and flourish among the stars.